this lecture, we'll be going over Chapter 2, the Chemistry of Life. Now, there's a variety of expected learning outcomes for this chapter, and I know chemistry can be a bit daunting. However, we're only using the basics for chemistry that we need for anatomy and physiology. So remember, this isn't a chemistry course, but we do need to have a foundational knowledge in this subject. So let's start with the chemical elements. Elements are the simplest form of matter to have unique chemical properties that cannot be broken down by ordinary chemical means. There are 91 elements that are naturally occurring, and each of these elements has a building block called atoms. We want to focus on the 24 elements that have a biological role. 6 of those elements make up 98.5% of body weight, and those 6 elements are oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. We also have elements in smaller amounts called the lesser and trace elements. The lesser elements make up about 0.8% of the body, whereas the trace elements make up less than 0.7%. And these are required in minute amounts and are found as part of enzymes. Our minerals are inorganic elements that are extracted from soil by plants and passed to humans. They make up about 4% of the body weight. It's mostly calcium and phosphorus, but we do have other minerals in the body like magnesium. These are important for body structure and enzyme function. We find calcium in crystals in the teeth or calcium in the bones. And we have electrolytes, the mineral salts that are needed for nerve and muscle function that we'll learn about later in the semester. So let's look at the atomic structure. Atoms have 3 separate components: protons, neutrons, and electrons. We use, in this case, planetary models to show the differences in the number of protons, neutrons, and electrons for each of the different elements. As we can see here, we have a different number of those for carbon than we do for sodium. Protons are going to be our positively charged subatomic particle that's found in the nucleus. Protons are what helps us determine the atomic number of an element. So, for example, hydrogen only has 1 proton, therefore its atomic number is 1. Carbon has an atomic number of 6 due to its 6 protons, and oxygen has an atomic number of 8. Neutrons, on the other hand, have no charge. They're neutral. They're found in the nucleus with the positive protons. Now, we can calculate our atomic mass by taking the number of neutrons plus the number of protons and putting them together. However, different elements can have a different number of neutrons, and we call those differences isotopes. Let's look at the isotopes of hydrogen. Hydrogen has an atomic number of 1 due to its 1 proton, and an atomic mass of 1 because it only has 1 proton and no neutrons. However, the isotopes, deuterium has an atomic mass of 2 because it has 1 proton and 1 neutron, and tritium has an atomic mass of 3 because of its 2 neutrons and 1 proton. So for hydrogen, we had 3 different atomic masses. We can take the average of those masses and figure out the atomic weight for an element. Now, most of these isotopes are stable. However, a few of them will disintegrate and give off energy. We call those radioactive isotypes or radioisotopes. They have intense radiation that can be ionizing. They're ejecting electrons and destroying molecules. And this can lead to genetic mutations and even cancer. However, we can use these radioisotopes for radiation therapy and diagnostic procedures. For example, if we're trying to look at thyroid activity, we can use radioisotopes to help us visualize that. Our last subatomic particle is electrons. They are negatively charged, and they're found in shells or energy levels around the nucleus. Now, there's a certain number of electrons that can fit in each of these energy shells. In our first shell, closest to the nucleus, we can hold up to 2 electrons. In the next shell, we can hold up to 8. In a neutral atom, the number of electrons and the number of protons are equal. We'll learn later what it looks like when those numbers are not equal. So we can see here in our planetary models that in our first ring, we have 2 electrons, and in our second ring, we only have 3, but we can have up to how many? 8, as we said in the last slide. And so we can see that we can fill each of these. For example, with sodium, we filled the first ring with 2 electrons, the second ring with 8, and our third energy shell that can also hold up to 8 only has 1 electron in this case. So if an atom gains or loses an electron, then we call it an ion or electrolyte. And we can have positively charged ions called cations or negatively charged ions called anions. Let's look at some examples. Sodium, as a neutral atom, has 11 protons and 11 electrons. However, if sodium loses an electrons, we will still have the 11 protons, because if we change the number of protons, we no longer have sodium. But we'll have 1 less electron, so we have an imbalance. So if we have 11 positive and 10 negative, we are left over with 1 positive charge, a charge of positive 1. And we can write that as Na plus 1, or we can do the shorthand where we only put the positive sign. We can look at an example of an anion. Let's look at chlorine. Typically, a neutral atom of chlorine has 17 protons and 17 electrons. However, if chlorine gains an electron, then we have 17 protons, because they stay the same, and 18 electrons, which leaves us with an overall charge of -1. So an ion is a charged particle with an unequal number of protons and electrons. Ionization, however, is when we have a transfer of electrons from one atom to another. So we have our octet rule, which is we want each of our energy cells to be full. That inner cell to be full with 2 electrons, the next shells to be filled with 8 electrons. In this case, we have our sodium, its inner shell is full, its second shell is full, but its third shell only has 1 electron. Well, how many electrons does it want to have? It wants to have 8. So how many more electrons would we need in order for this outer shell to be complete? We would need 7 more. But let's look at chlorine. Chlorine has 7 electrons in its outermost shell. How many does it want to be complete? 8. So it's only missing 1. So what we have is a transfer of electrons, that ionization. Sodium will easily give up 1 electron so that its outermost shell will be 8. And chlorine will gladly accept an electron so that its outermost shell will be 8. But now that sodium has lost an electron, has it become a cation or an anion? Chlorine is gaining an electron. Has it become a cation or an anion? Well, remember, the anion is the particle that gains an electron. It will have a net negative charge. So chloride is going to be our anion, and sodium is going to be our cation. Now, we formed 2 separate charges, positive and negative. Opposites are attracted to each other, and these 2 are going to come together to form a bond that we will learn about in our next video. Electrolytes are going to be substances that ionize in water, which means they break apart. And they form solutions that are capable of conducting an electrical current because of those positive and negative charges, when they break apart into cations and anions. Electrolytes have a huge importance in the body for chemical reactivity, osmotic effect, electrical excitability of nerves and muscles, and so forth. So it is very important to maintain an electrolyte balance in the body. Lastly, we have some terminology. Molecules are chemical particles composed of 2 or more atoms united by a chemical bond. A compound, on the other hand, is a molecular compound of 2 or more different elements. We have molecular formula. This is going to identify the constituent elements and how many atoms of each are present. And then our structural formula that tells us the location of each atom. That's all for our first video. Please go over to our next video for part 2, where we start looking at chemical bonds. See you then.